Hello, I'm going to share what I've learned through this course on a concept called principal component analysis, aka dimensionality reduction. And I know that's a mouthful, but I can at least try to simplify it for you. Maybe not give you a complete 100% accurate explanation. For that, you probably want to. I'd like to recommend this particular course. The people at this who created this course were kind enough. I actually reached out to them and asked them for permission to show some of the examples through these videos and such during my machine learning journey. And they agreed to, they allowed me to at least show some examples here. So, but I'm not going to give away, a lot of the trade secrets or a lot of the total in-depth detail for the course, because this is one of those things I'd recommend that you really need to go out and purchase. They worked very hard for this. As you can see, it's a 41 hours of demand video. I've learned so much from this course. I've went pretty much from almost zero knowledge in this to the point now where I understand the algorithms, at least from a high level standpoint. I went through a numerous series of labs, and I feel like I have enough of an understanding of this now where I could sit down and talk and participate in meetings and determine if certain aspects of machine learning may or may not be valuable for an organization, depending on the business problem that you're trying to solve, things of that nature. And I feel if you take this course, you'll have the same type of knowledge. So as a favor, as appreciation to them allowing me to show you some of the things here, I do sincerely say that this is definitely a course worth taking. So having said that, one of the concepts or one of the key elements in machine learning is that of dimensionality reduction. And one of the key aspects of dimensionality reduction is principal component analysis, which is PCA. So the main idea behind PCA is to reduce the dimensionality of a data set. So what does that mean? So if your data set has many different independent variables, and they may or may not be correlated with each other, heavily or lightly, we want to reduce that number of independent variables to a much smaller number, including just those variables that really, truly, significantly impact the outcome of the prediction. So at times you may be presented with a bunch of information that a lot of it's noise, a lot of it's, how do I want to say it? There's a lot of data. The more independent variables you have, the much longer it's going to take to run these predictions and train your model, and that could cost you a little bit more in the end result. CPU time, especially if you're spinning up clusters in the cloud to do that kind of stuff. So basically, it transforms this data set that has, potentially maybe 50 independent variables, and it based on these calculations, PCA or LDA or kernel PCA, they've all used different techniques to do this reduction. It'll end up with a data set that may take those 50 variables and say, hey, based on these 50 variables, we feel that only 7 of them really matter for what you're trying to solve. So we've just basically gotten rid of 43 of those because their weights really didn't significantly impact the problem. So now you can take that data set and work with the 7, and your model will be trained much quicker. And the end result is, less cost. It'll be quicker to do your predictions and things of that nature. So having said that, I'll just give you a quick demonstration. So here's our data set, and for this particular lab that they gave us. And in order to show this to you in a better way, I have Spider open. And what I'm going to do right here is I am going to at least run these lines up here. So we'll get our variable explorer right here. So we see our data set. So instead of showing you this, I'm just going to show you a transformed variable using the Panda library to read that in. And so instead of showing you the CSV file, we have now created this from it. So to explain the problem in a little bit of detail, we have all of these are different wines. So the way the course explains it with this, and this is a open source data set too, by the way, that you can download. But the way they explain this is you have each row is a specific wine, and each wine has all of these different chemicals that make up that particular wine and the composition of each of those chemicals. And at the very end, you have a customer segment. And the values in this customer segment, as I scroll down, is basically 1, 2, or 3. So the way they paint the picture is, imagine that a business owner for a particular wine shop or whatever has accumulated and grabbed all of his or her data, including all of the makeup, so where each row is a specific wine that they sell. And so they've gathered all of the data for each wine, as well as the chemical makeup, the compounds and things of that nature. And they were able, through their own techniques and their own means and all that, identify their own customer segment that tended to, buy this particular wine. So the business owner identified 3 different customer segments. So we got 1, 2, and 3. And each of those segments preferred certain types of wines that had these particular chemical makeups. So the idea here is to train a model, given, basically to train a model with another set of features and such, just to see which particular segment that they would belong to. So as you can see here, we have a lot of independent variables. Each of these, for the most part, are the chemicals. We've got about 13 in total. We don't, with dimensionality reduction, we don't really want to train our model with all 13 if we can avoid it, because in some real-world situations, again, you may have 50 to 100 or more, and that's compute intensive. So what we would like to do is to try to see out of all these 13 that make up specific segments here, what are the weights of these? Can we do away with some of these in such that we only need maybe 3 or 4 to pretty much come up with a very accurate segmentation count here? And if we can, then our new trained model is going to run that much faster. So in a nutshell, that's the idea behind dimensionality reduction. Now, there's a couple of kinds of dimensional reduction techniques. One is PCA, which is this here in this example, principal component analysis. That uses a feature selection called backwards elimination, which is a different way of, it's basically trial and error by calculating error rates. So you're going back and reiterating over and over again. And then there's another one called LDA, which is, it's kind of like, I'm trying to remember, I think it's like linear discriminant analysis, and that uses the whole concept of forward selection. And then you have bidirectional elimination being used for another extraction technique called kernel PCA. So those are all different ways to perform dimensionality reduction. So going forward on this particular example right here, what we're going to do is, now that we've created our X here, we've got our X right here, and then we have our Y, which is our dependent variable, which is our customer segment. So we've split apart that data set. What we're going to want to do now is we're going to split this out into our training and our test set. And that's exactly what I've done right here. So, we have our test set right here. It's our Y test. And we have our training set, our Y train. And of course, we've got our X test and we've got our X train. Refreshing your memory again, we want to take our originals data set and split it out into our training and our test set, because we're actually going to train the model with our X train and Y train. And when we train it, we're going to want to run the results of that model, validate it, and see what the accuracy is off of our test set. So our X test and Y test, again, this is original real data that comes from our data set. So that's a typical real world scenario. Test size, basically here we say 0.2. Again, you can make that from 20 to 40%. Ideally, 20% is what you want your test set to be. There's no true trial and error kind of a thing, but it seems to be the recommended approach. So that's that step. One of the most important things that we want to do is feature scaling when we're doing something with dimensionality reduction. So you may ask yourself, what is feature scaling? Well, we just basically applied feature scaling to our training set, our X train and our our X train and our X test set. So as you can see, we took all those whole numbers now and we've actually reduced them. So the main concept of feature scaling is to size, normalize all of our independent variables. So some of these independent variables that we have are somewhat unrelated to each other. So, and some of them may have much, much larger values than the others, but just because they got much, much larger values, it doesn't mean that they're that much more weighted. What we want to do is we want to take all of those and kind of shrink or set, resize, reshape, and normalize them all so that they're all pretty much scaled to one another in such a way where you don't have one that's massively, completely influencing another one just because a number happens to be higher for those specific type of ranges for that variable. It is a little bit complex to describe, but the idea behind that is you want to get everybody on the same scale, if you will, all the different variables. And so they call that, normalization and things of that nature. So we do want to apply normalization to this. Now, another interesting thing here is, we may have 13 features in our data set. So if you take a look here, I believe we do have 13. So after having performed this feature scaling, we're going to apply PCA. So assuming this is our first time through on this data set, we don't really know how many components we're going to need initially. So what we can do is we can apply PCA right here, and we'll just use 13. Let me go ahead and run this again. Okay, so I had to highlight that whole section right up there. So I'm going to start out with 13. Basically, I'm going to take the whole set and go against the PCA library from the Skylearn Python library. So what we end up with is, after doing the fitting and the transform, we end up with this explained variance, and that's kind of an interesting variable right there. But what that basically did is it took all 13 of our independent variables and it sorted them in descending order by the most significant impact to the least significant impact. And so the idea behind this is you can see right off the top, we've got 3. The first one is like 36%, the second one is 19, the third is 10. And then you kind of got the rest of these, which are under 10%. So this is where you kind of glance, eyeball, and look at it, and then you kind of say, well, what if we go ahead and train our model with just the top 2 and then ignore the rest here? So let's go ahead and try that. So what we want to do now is we're going to want to change this to 2. And what I like to do is restart the kernel every single time. So that just basically resets our library again. And so now our kernel is restarted. And what I'm going to do is run this again with the value of 2. And so now, as you can see, our explained variable variance just contains these 2 in this particular PCA model. And what we've done here is we've actually applied logistic regression, which is our curved regression, to this. And we've done predictions on it. So the idea behind that is, we have our test set and our training set. So here's our X train, and here's our Y train with our predictions right here. We've reduced this down to 2 dimensions, and so it's 2 independent variables. And then, of course, we've got our Y prediction. So this is what our model predicted, and this is what our actual data said right here in the Y train, and this is what our model basically predicted based on that if we were to reduce this down to 2. So as you can see, it's not completely perfect, but it's done a decent job at it. So we've got our Y train, Y prediction right here. So what if we go ahead and run our confusion matrix? And I like to, the confusion matrix itself will go ahead and explain the accuracy for the most part of it. And as you can see, for our predictions and our actuals and things of that nature, you know, it did an okay job. So how to read this? Okay, so I stand corrected. I think I was showing you a different, let's see, I think I was showing you the Y here, which didn't look to be as accurate, so I apologize. So here we have our Y test and our Y prediction right here. Now if you look here, the prediction as opposed to the actual right here, they are pretty darn accurate, which is really good. So what we've been able to do is we came up with a confusion matrix right here, and kind of the way to read this is when you go diagonally, because we've got two features now. When you go diagonally, that's a number of correct predictions, or that's a number of correct results. And then the ones in the red here are incorrect. So what this basically is saying is we have a total of 36 observations if you go ahead and sum up all of these. So 14 plus 15 plus 6 plus the 1. Yeah, it's a total of 36. And if you sum up the accurate ones, it's 35. So the idea behind there is if we say 35 divided by 36, that's 97%. So what we've been able to do, what that basically means is by taking our original data set of all 13 of these independent variables, and by applying PCA to dimensionally reduce that just down to 2 independent variables, using the top 2 that you saw here by the explained variance, we're able to create a model that's, you know, about 97% accurate as far as identifying the customer segments. That's pretty good. And when you go from 13 down to 2, you're going to significantly speed up your set here. So another interesting thing is, what if we were to choose 3 instead of 2? So what if we upped it up 1? So I'm going to restart the kernel right here. And then I'm going to apply 3, because if you remember, when I originally showed you in the past, the top explained variances, really the top 3, the third one was like 10%. So now let's go ahead and try that again, where we have this as 3, and let's see what our confusion matrix shows us. So now if you look at our confusion matrix right here, you can see we got a 100% accuracy, which is really, really good. And so now if you add 4, 5, or 6, it's still going to be 100% accuracy. Why add all 13 in your data set? Why go through all that extra calculation and time when really, if you want to apply close to an approximately 100% accuracy, you only need 3. So you kind of get the idea right there. And which is kind of nice in this lab, in this example, is they'll show you how to plot out the results. So 1 second here. Okay, well, right there, just to make it quicker, it's because I changed the number of components to 3 right here. I didn't really want to go ahead and do the plots with the mesh grids with the extra dimensions. So I just want to go ahead and rerun this again, so you'll be able to see just how accurate our results are right here, which is kind of cool. So here's our training set. As you can see, here's our blue and here's our red. These are all different segments, and we're pretty accurate. We just only have 1 green, 1 data point that should have been green that falls into this category, and we have only got, you know, so it's really accurate. It's a and then if we apply our test set, so that's how we trained our model. Now if we apply our actual test set right here, this is that confusion matrix right here, where we have just the 1 inaccurate per prediction right here, and that would be this green. So pretty good, and I hope this gives you an idea of what dimensionality reduction is, and as well as what principal component analysis is. And if you can see right here, this is thanks to the Udemy course, as you can see right here, a lot of the mathematics is encapsulated from you, especially with PCA. You know, it's got its own Python libraries here. You just basically need to set things up. And what else is kind of cool in Spider is if you hit Command I right here, on a given, basically, let me go right here, on a given, you can highlight, and if you hit Command I on a given thing right here, so it's going to be a stickler for me right now. There you go. I just did it right here for the standard scaler. As you can see, in some cases, it's actually going to bring up the online help. So it'll show you what all the different arguments are and attributes. So that's just another cool little thing here. So I hope that helps. And please do consider buying the course, because I've learned a lot, and I feel that you will too. And thanks for watching, and have a great one. Bye-bye.